So this one's going to be this is going to be a much shorter one, much shorter lecture than the previous two. So we are continuing with our theme of using definite integrals to construct geometric quantities. Now we are going to use the definite integral to find the length of a curve. So suppose that we have the graph of some function, and we are restricting our attention to values of x in the interval a to b. Such an object is called an arc, by definition. If you take some portion of a graph, that's called an arc. Now, if the function is linear functions can be written like this, ax plus b, then its graph is a line. Consequently, any arc from that graph is a line segment. If that line segment connects these 2 points in the xy plane, then we can figure out the distance between them, because we have the distance formula. So recall the distance formula here. So this is the distance, or rather the length, of the line segment connecting these 2 points. So if our function is linear, then we're done. We just use the distance formula immediately. So of course, it's going to be more interesting to consider the case where the function is not linear, in which case its graph is not a line, but some sort of curve. So the question arises, what is the total length of any arc drawn from that curve? So let us suppose that this function is differentiable. That's not a bad assumption to make. I mean, we're used to taking functions and taking their derivatives, so let's just assume that this function is well behaved enough that its derivative exists. Now, what does it actually mean geometrically for a function to be differentiable? Well, it means that we can draw tangent lines to the graph. Put another way, if a function is differentiable at a point, and then we zoom in to that point on the graph, eventually, if we zoom in far enough, the graph is going to look like a line. Specifically, it's going to look like the tangent line. Let me show you what I mean by bringing up GeoGebra for a second. Let me show you what I mean. So let's just take some random function. I don't know, let's say f of x equals sine x. Sine x is differentiable, certainly. I mean, its derivative is cosine. So I claim that because this is differentiable, if we zoom in far enough, the graph is going to look like a line. And hey, wouldn't you know it, that sure looks like a line to me, right? So this line that we're looking at here, if we were to take this line and extend it indefinitely in both directions, that would be the tangent line at this point. Let's pick another point at random to zoom in on. Let's say here. Well, if we zoom in far enough, indeed, it looks like a line. And you can do this with any differentiable function. Oh dear. You can do this. Oh, why is it screwed up? Whatever. You can do this with any differentiable function, that if you zoom in on the curve enough, eventually it's going to look like a line. And lines are easy. We can find their lengths using the distance formula. So, we have a strategy. If we want to find the length of an arc that has been taken from the graph of a differentiable function, what we can do is we can split the curve into a bunch of tiny little pieces, and then if the piece is small enough, we can assume that the function is a line segment on that piece. So that instead of a curve, really what we have is a whole bunch of little line segments. So what we can do then is we can figure out the length of each line segment. and then add up the lengths of all of those little line segments. And when I say add up here, of course I mean integrate, because we are taking these line segments to be infinitesimally small. So that is our strategy. Break up the curve into tiny little pieces, and if the pieces are small enough, we can imagine they're line segments. Therefore, we can take their length and then integrate up all those little lengths. So that begs the question, what is the little length going to be? What is the thing that we're going to be integrating? So let's see. Suppose we have some function, some arc, because we're restricting ourselves to a finite portion of its domain. And let's take 2 points on this graph that are really, really, really close together. So close together that the graph is effectively a line segment in this region. Namely, we'll take the point xy on the graph and the point x plus dx, y plus dy really, really, really close to it. So dx and dy are infinitesimals. So very, very, very small, but still non-zero quantities. So the assumption is that the graph is linear where it connects these 2 points. Therefore, the length of the line segment connecting these points, which I'm going to call dl, d because it's an infinitesimal quantity, is given by the distance formula. So, what is the distance formula? Well, it's the difference in the x-coordinates. So in this case, we have x plus dx minus x squared, and the difference in the y-coordinates squared. So the difference in the y-coordinates is y plus dy and y. Take their difference and then square them. So we can see that the x's, this plus x, this minus x cancels out. This plus y, this minus y cancels out. So the length of a tiny little line segment is dx squared plus dy squared square rooted. Now, how do we deal with this? Because again, remember, an infinitesimal isn't actually a number, it's a formal symbol. So this thing that we have right here, we can't actually work with. We want to eventually end up with something we can integrate. So you may remember from the previous section, when I was talking about the washer method, how an infinitesimal squared is effectively 0. Because if dx is the smallest number that we could possibly measure, then dx squared is so small that we can't measure it, so we have to set it equal to 0. Well, that's not really going to work here, because if we just take dx squared and dy squared and set them both to be 0, then, well, we just have the square root of 0, which is 0. And we've gotten nowhere. I mean, this quantity has to be non-zero, or else we're adding up a bunch of zeros, and that gives us nothing. But this isn't strictly accurate, because that neglects the effect of the square root that we're taking. So indeed, suppose that dx and dy are approximately the same. At the very least, they have the same order of magnitude. So like, if dx is the length of an atom, for instance, if that's the smallest length that we can measure, then dy also has that magnitude. So, if that's the case, then dx squared plus dy squared is approximately 2dx squared. And then what does the square root do? Oh, that gets rid of the square. So dl, the length of our little line segment, has the same order of magnitude as the infinitesimal to begin with, which is non-zero by assumption. So we can assume that this guy is non-zero, and that's consistent. Because the square root, if dx squared is so small that we can't see it, well then the square root is going to make it bigger again, to the point where we can see it again. But regardless, we need to rewrite this thing so that it's in a somewhat useful form. Now I'm going to do a little bit of algebraic magic. Don't think too hard about this. This isn't a strictly rigorous mathematical argument. This is more like the way that a physicist would do things. But trust me that this captures the core of the argument. And the important thing is that the formulas we get in the end are still correct. So we have this. Multiply on the inside of the square root, dx squared over dx squared. So this is just 1, right? So we can put that in there without any trouble. Now take the dx squared in the denominator and distribute it to get dx squared over dx squared, dy squared over dy squared. So that's the one on the bottom that I distributed. And then the one on the top, I'm going to pull out of the square root, right? So dx squared square rooted is just dx, okay? So this one on the bottom ended up here. I distributed it. This one on the top, I pulled out of the square root. Now, dx squared over dx squared, well, that's 1. dy squared over dx squared, well, that's dy dx squared. But hey, wait a second. dy dx, that's a derivative. Namely, it's the derivative of the function. Right? There's something magical about the notation we use here, where if we assume that dy and dx are infinitesimals, they're arbitrarily small non-zero quantities, then their ratio is exactly the derivative. You can formulate the derivative in terms of infinitesimals as well, and then the notation is consistent. Suffice to say, we end up with this formula. So the length of a tiny little line segment on the arc is given by this formula, root 1 plus the derivative squared dx. Consequently, to get the total length of the curve, we integrate all of these little pieces. So we add them all up. So this is the integral that we end up getting. So the integral of root 1 plus derivative squared dx. And that is if we are given a function in the form, or a graph in the form y equals f of x. Of course, if it was the other way around, if we had x equals a function of y, then the argument is exactly the same. It's just that the variable of integration is now y instead of x. And yeah, I remind you again, these arguments aren't strictly rigorous, but it captures the core of the correct argument. If you have the Stewart book, you can find the real proof, but I don't think it confers any additional insight, really. In any case, when I first learned calculus, I learned it the way that I'm telling it to you here with like these infinitesimals. And frankly, this is how they do it in physics. Like, in physics, people don't worry all that much about the mathematical correctitude of their arguments. These arguments with the infinitesimals are all they need, and it ends up giving correct formulas anyway. So I wouldn't worry about doing perfectly correct mathematical arguments until you're like in graduate school. So I think this is good enough. All right, so a couple examples. So find the length of the arc of this dude. So this is an equation that gives some sort of curve in the plane. Doesn't really matter what it looks like. You can type this in GeoGebra if you want to see it. All you need to know is that it's a curve, and it extends from the points 1, 1 to 4, 8. So let's find the length of this arc. Well, first off, we're going to need to take the derivative of some function, which means we're going to have to rewrite this to be in the form either x equals f of y or y equals f of x. So I suppose it's up to you which one you want to do. So you can either take square roots of both sides to isolate y, but taking square roots sort of makes me queasy because you always have to wonder about that. Taking square roots of both sides, sometimes you have to put in a plus minus. So I think I would rather take cube roots of both sides, because cube roots, you don't have to worry about putting in plus minuses. So let's write the equation in the form x equals f of y. So we get x equals y to the power 2/3. Okay? And then what is the range of y? Well, so I'm choosing to let y be the variable of integration here. So y goes from 1 to 8. But before we do that, we're going to need to take the derivative of this thing. So x prime is the power rule, so 2/3 y to the negative 1/3, right? Because 2/3 minus 1 is negative 1/3. And then furthermore, we're going to have to square that. So let's actually go ahead and plug in the full formula now. So y is going from 1 to 8, square root 1 plus, and then the derivative squared dy. So let's see. So what happens when we square this? So 2/3 squared is 4/9. And then this becomes y to the minus 2/3. Okay. Well, I appear to have written myself into a corner here because I don't know how to do this integral. I really don't. I mean, you can do it numerically, of course. There's no problem there. But alas, I'm not aware of any analytical method of doing this. So maybe my choice of writing this as x equals y to the 2/3, maybe that wasn't a great choice after all. So let's do it the other way around and see if that's better. Let's see, can you? See, now I'm actually thinking, how can we evaluate this? I'm not convinced that it's possible. Well, maybe you can do it. Well, I don't know. So, let's try writing the equation to be of the form y equals f of x instead, and see what that gives us. So, to solve for y, we would need to take square roots. Okay, now, like I said, taking square roots makes me queasy, because really we should be putting in a plus minus here. But let's think about it. We are only interested in points between 1, 1 and 4, 8. So this arc is entirely contained inside the first quadrant of the plane. In other words, everything is positive. We are only interested in the positive branch of this curve. So we can just assume that we're taking the positive branch, and there's no problem. So since the curve, so let me just mention that. So ordinarily, I would write y equals, plus minus x to the 3/2. But the portion of the arc we are interested in, so right, if there's a plus minus, then that means we actually have two functions. But the portion of the arc that we are interested in is in the first quadrant of the plane. That is, everything is positive. So we can ignore the negative branch of the root. Okay, so y equals x to the 3/2, and we can convince ourselves that that's okay. So what are the ingredients? Well, we need the derivative of this dude. So the derivative is 3/2 x to the power 1/2, right? Because 3/2 minus 1 is 1/2. So the integral becomes, well, let's see, the variable of integration is x now, so x ranges from 1 to 4. big square root, and then 1 plus all of this junk squared. And hopefully this will give us an integral that we actually know how to deal with. So let's see, 3/2 squared is 9/4. Oh, well, how convenient. X to the 1/2 to the power 2 is just x. Now, this is indeed an integral that we can do, namely by U substitution. So, in particular, let's let U be all the junk underneath the root. Right, so let U be 1 plus 9/4 x. Then, so in the method of U substitution, once you choose U, you then have to take its derivative. The derivative of this dude is 9/4. You then need to solve for dx. So dx is equal to 4/9 du, right? So take the dx, move it over here, and then divide both sides by 9/4. Now, because we're dealing with a definite integral, we're going to need to change the bounds as well. So change the limits of integration. So let's see. When x is equal to 1, right? So the lower limit is 1. So when x is equal to 1, what is u? Well, u is equal to 1 plus 9/4 times 1. Oops. And that is, what is that? Common denominator is 4. 4 plus 9, so 13. So that becomes the new lower limit. What about the upper limit? Well, when x is equal to 4, u is equal to 1 plus 9/4 times 4, which is the same as 1 plus 9, so that's 10. So finally, our integral becomes the integral from 13/4 up to 10 of square root u, and then instead of dx, I'm going to put in 4/9 du. 4/9 is a constant, so I may as well put it out front. And then du, like so. Whoops. Okay, so now we just need to do the power rule. So this is the same as u to the power 1/2. So adding 1, we get 3/2. Dividing by 3/2 is the same as multiplying by 2/3. Evaluate that between 13/4 and 10. This is going to get ugly, but it's certainly doable. Let's factor that 2/3 out first. So 4 times 2 is 8, 9 times 3 is 27. And then we have 10 to the 3/2 minus 13, oops, minus 13/4 to the 3/2. And is there anything else we can do with that? I'm not really seeing any easy way to simplify this. I suppose one thing you can do. So I mean, whatever. This is good enough, I think. Oops. So if you're interested, you can give an approximation to this. So hang on, let me quickly compute that. So that's about 7.6337. So I would be fine with this. Just to be pedantic, though, let me let me write it down the way that the book has it. So, oh, this is really pedantic, but I suppose I should show it to you. So 10 to the 3 halves, that's the same as what am I trying to say? 10 to the 3 halves is the same as ten to the 1 plus 1 half, right? 1 plus 1 half is the same as 3 halves. Same situation here. This is really stupid. I don't like this. But this is how the book did it, so I need to show it to you. So that just in case you have the book, or just in case one of the multiple choice answers is really weird, you sort of know what's up. Similarly, 3 halves is the same as 1 plus 1 half. So one way that you can write this, so addition in the exponent is the same as multiplication in the base. So that means this is the same as ten times root 10, right? So 10 to the 1 is 10, 10 to the 1 half is root 10, and same situation here. So 13 root 13, 4 root 4. Now we can go a little bit further. This is so stupid. I hate this. This sort of algebraic nonsense is part of why I didn't really like using this book in the first place. But I suppose I should show you this sort of tomfoolery at least once so that you know what we're up against. Because now we can factor this 4 root 4 out, because the square root of 4 is just 2, right? So this is 4 times 2, which is 8. So 8, like so. So now we can factor out that 1/8. Right? We can factor out that 1/8. So we get this times 8 minus 13 root 13. Then 8 over 8 cancels. So we have just 1 over 27. And then there we go. So that's the way that the book writes it. That's the way that the book writes it. I think that's dumb. I think this is perfectly fine. So yeah, I hope the multiple choice questions just give you answers that are in this form. If so, I'll choose the homework such that they do that, because this sort of algebraic hand wringing is really stupid to get it down to this form. Anyway, point being, there's not too much that you need to do. You just need to find a function that represents the curve, differentiate it, and then write out this integral. And then solve it, if possible. So in this case, we were able to solve it by doing a u substitution. But hey, spoiler alert, the sort of integrals that come from arc lengths very often actually aren't solvable at all. Or at least they're not easily solvable. So in these next two examples, I say just write the integral that gives you the arc length, and then don't bother trying to figure out what it actually is. I mean, you could use like Simpson's rule if you want, if you really want to put a number to it. But in general, the integrals that you get from this procedure are either extremely difficult or straight up impossible to evaluate by hand. And this was sort of a, this example was sort of hand-picked so that you would end up getting something that you could actually do. But that is the exception rather than the rule. Let's see. Okay, so we've been given x as a function of y. So let's make y our variable of integration. So we're going to end up doing taking this form. So we need the derivative of this function. So x equals y squared. So we need the derivative. Well, that's easy enough. The derivative is 2y. Yeah, and then we just fill out the rest of it. So y varies from 0 to 1. Big square root 1 plus derivative squared dy. So 2 squared is 4. Yeah, and let's just leave it at that. Incidentally, we will be able to solve integrals like this later on in the course using a trigonometric substitution, but we don't know how to do that yet. So I don't want to say solve, I want to say evaluate. So that's section 7.3, I think. 7.3 or 7.2, I don't remember. In any case, we'll be doing that later. Yeah, that's 7.3. So we'll be doing that later. For now, it suffices to say that this integral gives it to you. And then you can use like Simpson's rule or trapezoidal rule to actually put a number to it. Okay. So write an integral giving the length of the arc of the hyperbola defined by xy equals 1 from the point 1, 1 to 2, 1/2. Okay, so let's write this as a function. So I suppose we have the choice of which variable we want to use. Let's go ahead and choose x. So let's write this as y equals f of x, just for fun. We could do it the other way just as easily. So if we wanted to solve this for y, just divide both sides by x. Now we need the derivative of this. So this is x to the power -1. So derivative. So the derivative of that is minus x to the power -2. So that's that. So let's see, x ranges from 1 to 2. 1 plus, and then the derivative squared and then we could just clean this up a little bit. So this -1 gets squared away, and then 1 over x squared squared is the same as 1 over x to the 4th. And that's that. Incidentally, I don't know how to solve this one at all. This one might actually not be possible to do by hand. So you would have no recourse but to use numerical integration. Okay, so that's all that I have to say about this section. Really, it's pretty simple, I think. So take the equation that you were given, write it as a function. You know, you have the choice of how you want to do that. But write it as a function. Once you have done so, you have to take the derivative of that function, and then you just plug it in. Now, the question of evaluating that integral is another question entirely, but setting up the integrals in the first place is at least fairly simple. You just follow the recipe. And you don't need pictures either. Like, you could get pictures of these graphs if you want, but that doesn't really add any enlightenment. Okay, thank you.